All right, jumping right in. What did we learn in lab yesterday? What did you learn in lab yesterday?
Light acts as a particle.
Light acts as a particle. Good, because that is the primary thing we wanted you to learn. How do we know that light acts as a particle?
Because of the photoelectric effect.
Okay, yeah, because of the photoelectric effect. Which means that we have the energy of the electrons that were liberated by a photon, by a particle of light, that was proportional to the frequency. And so the theory, one thing, why don't we have photon energies absorbed by one electron? It comes off with twice that amount. That's just a statistical calculation. You have so many electrons spread out in your metal, the chances of a photon hitting, or two photons hitting one electron is very small because the photons are really little tiny volume. All right, what's the volume of the photon? I'll never ask you that question because I don't know if there is an answer. Basically, you have to be exactly the right point. So the chances of two photons being exactly the same point is very small unless you have super high intensity. If you have super high intensity, then the probability of a multi-photon event becomes reasonable. So that's why the assumption was made that it was only a single photon. So we had good evidence there in yesterday's experiment that light is behaving as a particle, each particle having energy E equals hf, where h is Planck's constant. Did you all find Planck's constant with a reasonably small percentage error? Good. That was the goal. You didn't let Al down, as it said in the lab guide. So now a question that's just out of the blue. Not a question that you are prepared for except for with your reading quizzes. And that is, what are X-rays? So this is, like I said, it's out of the blue. What do you think X-rays are? Okay, I only heard two words from Mira: high energy. Who's present here? Lydia? Madison? You guys will be doing X-rays a lot someday. It's good to know what they are. In fact, Loma Linda's School of Dentistry magazine had a really good article about the history of X-rays because it's important to dentists who do them, use them a lot. Well, I didn't hear at least anyone give a definitive answer, which is fine. You haven't learned about them yet. X-rays are high energy photons. If you look at the electromagnetic spectrum, which I swear is here, there it is. If you look at the electromagnetic spectrum, X-rays are shown there. So they're electromagnetic waves, the same thing as a photon, right? A photon is a particle of light, which means a particle of electromagnetic radiation. So X-rays are particles of higher energy electromagnetic radiation. Now going back to all the slides I skipped over here, here's how an X-ray is produced. It's real simple. You have a high voltage source, and you have over here a heated filament. That is, this here, it shows it as a battery, but it's actually usually an AC source. About 6.7 volts AC is what's typically used. Going through a filament, that filament gets hot, and because it's hot, it's kicking off electrons. Those electrons have a negative charge, of course, and so you have, which side is positive in my voltage source here? The left side or the right side? You all knew this for exam number 1 this semester. The long side is always the positive side. And so that means this is positive, this is negative. Electrons with their negative charge are going to be accelerated across. And so those electrons, if this is voltage V source, then the electrons are going to have work is equal to Q delta V is equal to charge of an electron minus E times the change in voltage, which is going to be V source. And so that's how much work is done. And for some reason, I have a negative value there. I know that all my directions are right and my sign is wrong. Change in kinetic energy is equal to the net work. And so we end up with that's equal to the charge of an electron times the voltage of the source. I just dropped my sign error. I'm sure it's something very simple. I'm sweating now. I assume it's because I made a mistake and not because somebody turned up the thermostat. So you have an electron hitting with an energy of charge of an electron times the voltage, the source voltage difference there. And so usually we'll just say that energy in electron volts. Makes life easy. So if you have a 1,000 volt source, it has 1,000 electron volts. Well, when the electron hits the metal, what happens if a BB hits your body?
Cavitation. Wow.
That's a very fast-moving BB. In a general sense, the BB is going to slow down, and it's going to penetrate a bit, right? So there's a reason I didn't go with, a rifle shell or something. Or, yeah. Anyway, bullet from a rifle. So the same thing's going to happen when the electron hits the metal. It's going to penetrate a bit, but it's going to slow down. If it slows down, its energy has to go somewhere. That energy can go into a couple of things. It can go into heating, making it hotter, and it's going to. So that target is going to get hot, but it's also going to produce electromagnetic waves. That's a form of energy leaving. But we've learned that if these waves are treated as particles, that they would have an energy of HF for each photon, each particle that comes off. So if an electron hits and it has an energy of the voltage source times E, what's the maximum energy that a photon coming off could have? If it transferred all of its energy into one photon, what's the maximum energy it could have? Well, kind of. You have E equals HF equals change in kinetic energy, right? Because it's going to go back to zero. And so HF equals E times the voltage source. So that means that the frequency max, so HF is less than or equal because you don't have to transfer all of the energy. So F max is using the equal part. So you can calculate a maximum frequency that the light can have coming off. Could it have a lower frequency? What physical relationship would give it a lower frequency? Its wavelength is going to change with frequency, yes. But what going on with the electron would make it so it produces a photon with a lower than maximum frequency? Okay, I'll give it to you. It doesn't have to give all of its energy to one photon. It could, for instance, have a couple collisions, lose a little energy along the way. And so it could give any energy that's lower than that. So you can have any frequency that's lower than that, but that's the maximum frequency it could give off. And so when we look at the X-ray spectra, and yesterday I was going to look in the book to see if they've updated the picture. They had a picture that was just absolutely wrong for X-rays, which was rather disconcerting to me. But we'll look at a picture of that. There are two actual ways. Well, no, it's one way. When an electron slows down, the radiation gives off is called Bremsstrahlung. And I have it nicely spelled there because I can't spell Bremsstrahlung. It's a German word that means breaking radiation. So Bremsstrahlung. So this braking radiation is electromagnetic waves that are produced when something slows down. Anytime you have a charged particle slow down or speed up or change direction, what do we call slowing down, speeding up, and changing direction? Acceleration. So anytime you have a charged particle accelerate, it gives off radiation. And so this Bremsstrahlung is the name for the radiation when the particle is slowing down. And so the Bremsstrahlung radiation could be in any frequency from that peak that we found all the way down to a frequency approaching 0. So that means that we have a cutoff frequency. So here, this is actually shown in units of kilo-electron volts, but you could have put HF here on the same axis. And so there's a specific frequency with that. So this one here is shown with a wavelength marker for the minimum wavelength that corresponds with the maximum frequency. Remember, what's the relationship between wavelength and frequency?
Oh, see.
And so if you have the maximum frequency, that gives you the minimum wavelength. So that's why it has lambda min in there. So the Bremsstrahlung radiation is following something that looks like this. If you have energy on the horizontal axis, sometimes you'll have energy or frequency on the horizontal axis. Sometimes you'll have wavelength. If you have wavelength, it looks different because wavelength is not linear with frequency, it's inverse relationship. So the spacings look different. That's the error that at least was in the textbook the last couple of years, was they had the spacings for, I think they had the spacings for wavelength, but they had it labeled frequency. You know, they took the picture and marked it wrong. So the Bremsstrahlung is this here. Now remember, in theory, it could come all the way up. You could have frequency that's 0 produced. But in reality, you don't have much of that. It drops off. Then you have these peaks here. Those peaks are called the characteristic peaks. You see there it says characteristic radiation. The characteristic peaks are completely different. So the Bremsstrahlung is slowing down the electrons. The characteristic peaks are coming from nuclei of atoms. Instead of coming from the electron, they're coming from nuclei. If I have an atom, let's say the atom is copper. Copper is a common source for X-rays. If you have a copper atom, I have to get back here close enough to see. Copper has 29 protons in the nucleus. How many electrons is it going to have in the, I was going to say the nucleus, trick question. How many electrons do you have in a copper atom that has 29 protons in the nucleus? A neutral copper atom is going to have 29 electrons. And those electrons are going to be, for those of you who've already learned this in chemistry, we will learn this in physics in the coming weeks. You're going to have 1s, 2s, 2p, 3s, 3d, 4s, 3d. Your electrons are in those levels. And each level as you go down is going higher and higher energy. Well, if you take an electron and remove it, then another electron is going to fall down. Because electrons want to go to the lowest energy state possible. And so with this high energy electron, if it hits an atom, it can knock an electron out of the atom. So you can have a knock-on ionization. That's the name we give it, knock-on ionization. And so you can kick an electron out. And if you kick out an electron from the n equals 1 level, then you can have an electron from a higher level. In copper, we had n equals 1, 2, 3, and 4. You can have an electron from a higher level fall down into that n equals 1 level. And that electron falling down then is going to go to a lower energy. Energy has to be conserved. The energy leaves in the form of a photon. And so these characteristic peaks, here is idealized, here is something a little more realistic. Those characteristic peaks are peaks from electrons falling from a higher energy level to a lower energy level. And so the energies of those peaks are very distinct because they're telling you the difference in the two energy levels. And now we have some names for those. And I know I'm going forward for this class, but I know a lot of people know them. You have things like n equals 1, 2, 3, 4, 5. You guys familiar with that? What do you call the shell when n equals 1? You may or may not know. S orbitals are L equals 0. I just talked about this in Chad's quantum mechanics class yesterday, so he's like, yeah. It's called the K shell. 2 is called the L shell. What n equals 3 is called. Yeah, they're very tough with these. And so this is spectroscopic notation, just like the SPDFG is spectroscopic notation. And so you see here, that says K, characteristic radiation. Nathan?
So they still call the next one M because that would be kind of confusing.
Actually, I don't remember if they call the next one M. I stopped at the end of my memory. Just like I know that they skip either H or I for the SPDFG. It goes alphabetical order except for they skip one. I can't remember which one they skip. So I stop at G so I don't have to worry about which one it is that's skipped. So if it's a K, these ones here, it says K, that means that it's falling down to the n equals 1. Now, if it falls to n equals 1, it had to start from a higher value of n. So name a couple of values it could have started at. Very tough. 2 or 3. So we actually name these characteristic radiation. Notice this one says K alpha. This one says K beta. What does the AG mean?
Silver.
Argentium, silver, yes. So K alpha and K beta have different energies. The one with the bigger energy is the one with the, well, does it have a higher or lower frequency if it has a bigger energy? Higher. And if it has a higher frequency, what does that make its wavelength? So this one here with the shorter wavelength is a bigger energy. So K beta is a bigger energy than K alpha. That in and of itself may not be enough to give you the clue, but the number here tells you the shell it goes to, and then alpha means that delta n equals 1. Beta means that delta n equals 2. So a K alpha means it went from 1 plus 1 to 1. A K beta means it went from 1 plus 2 to 1. So K beta is 3 to 1, K alpha is 2 to 1. What would an L beta mean?
4 to 2.
Yep. So those characteristic peaks have a very simple meaning for what, the labels. And of course, the spectroscopic labeling, the K is telling you N, the alpha or beta is telling you the change in N. And so in this one here, it calls this K characteristic radiation. I think not. I think this one here is the K radiation, and this one here would more likely be L. Because if you go from 3 to 2, that's a much smaller change than if you go from 2 to 1. And so I think they've got that labeled wrong. Now, what do I know? This is an arse rendition. Who knows? But that's what X-ray radiation is. Why do they use X-rays so prevalently in the dentist's office?
To get a solid picture.
Okay, to get a solid picture, you said, is that right? Okay. Taking a picture, but they want to go through tissue in your body. visible light doesn't go through tissue all that well. I mean, it does a little bit. You can put a bright light on this side of your hand, and you can see light come through, and you can see the bones, right? So visible light would work somewhat. It's really, really intense for certain purposes. If you want to go through the entire body, it's not going to work so well. So they're using X-rays because X-rays, with their higher frequencies, can travel through biological tissue much more easily. And thus, they can see light X-rays coming through. And then they're taking a picture just like you would normally. So these days, I love it. The dentists just have a little CCD chip they have you hold in your mouth, and then they shine the X-rays in, and the CCD chip, just like what you have in your phone's camera, takes the picture that goes to their computer, and they have them instantly. They don't have to go through any developing. It's great. The technology advances are great. You guys will never know the pain of having those films that are way too stiff jammed into your gums for 30 seconds while you're trying to hold your head still. Yeah. Or maybe you do. Okay, we've already talked about the cutoff frequency, so we don't need to spend any more time here. Let's do a problem. A potential difference of 87 kilovolts is applied between the filament and the target in the X-ray tube used at the local clinic to look for broken bones. So we're going to emergency room or urgent care. What are the shortest wavelength X-rays produced by this tube? So calculate that quickly.
Oh no, I'm just.
Yay. Yeah, that's what I got. You check hers?
Yes. Yeah.
1, 2, 1, 3.
There's a couple things that communicate incorrect and has to do with units and the which are
It's also unit, so I did the answer right.
things that people have asked me about. The energy for a photon is equal to HF, where H is equal to 6.626 times 10 minus 34 joules times seconds. That's a 3.4. And yeah, that's where I made the sign error. It change of potential energy is equal to Q. That's where I made the sign error before. Oh, and I should put charge of an electron. And just for grins, 1 volt equals 1 joule per coulomb. we have an answer now that's more in the ballpark of 10 to the 14 to 16, somewhere in that kind of ballpark.
No. 19.
Okay, maybe that's right. I mean, 10 to 14 would have been visible. It's obviously not visible. Okay, you got 2 to 9 or 10 to 19 as well.
It's relative. Good, bad. It's true. What's a good synonym for relative?
Okay, we have some people are still making good progress. Some are done. Let's work this out. We have the energy of the photon is HF. And so that's what we're looking for is the F right there. We have the electron comes in, and for the maximum, all of its energy is transformed into the photon. So energy of the electron becomes energy of the photon. Put pH for photon so you don't get confused with proton. And so the energy of the electron is Q delta V, and it's actually going to be minus Q delta V, which makes it a positive. It's equal to HF. Therefore, F is equal to minus Q delta V over H. And I guess I should have put a minus sign. Electrons do have a negative charge. That's 19 there, times 87 kilovolts, divided by 6.626 times 10 to the minus 34 joules times seconds. Okay, my units got cut off, sorry. So I know a number of people did this calculation. What do we get for that frequency? DJ or Chad, I know you.
2.103 times 10 to the 19th power.
And now let's look at the units just to make sure that we are down with this. Our units, I had a coulomb on top, a kilovolt, joule times, and I'll drop the kilovolt over joule, that's a J, over joule times second. But a joule, no, coulomb, man, mistakes. Coulomb times volt over joule times second. The reason I wrote that is a volt is a joule per coulomb. And so that came out to joules on top. So now we can cancel our coulombs there, cancel our joules there, and we're left with 1 over seconds, more commonly known as hertz.
So for the top part, you would have had to change it to volts, right?
For where?
In the top part. Because I got that answer, but after I changed
Oh,
to 87.
from kilovolts to volts?
Yeah.
Yes. Or kilo means 10 to the third. So
Oh.
when you put it in, you put it times 10 to the third. Okay, so there we did a problem. I mean, we'd already done one where we see 87 kilovolts will give me this really high frequency, actually, 2 times 10 to the 19th hertz. Here's more pictures I put in for the characteristic peaks. Assuming one of these is K and one is L, which one would be which? Which set would be the Ks? You said which? Okay. That was what I took contest with the previous one. The Ks should be the ones with the higher energy. And the Ls would be the ones with lower energy. Because you're going to n equals 2, which is a much smaller potential energy gap than n equals 1. And then we have two peaks here for the K. Is this K alpha or K beta? Beta. Beta because it's going to be a bigger energy difference to jump 2 than to jump 1. So you can actually read them as long as you know there's none missing, you can read them. And so this would be K beta, L alpha, L beta. This here is the wavelength one. And like I said, I think the one in your textbook looks like the wavelength one, but it says it has frequency or something like that. What's the difference in having wavelength shown here? Well, the key difference in having wavelength shown here is and the space change. Because length 1 looks like a whale. So there's its tail. There's no tail on this. I'm just putting it there. With it blowing up a spout. Right? See why I like it? So that's what X-ray looks like. You have those characteristic waves, and you have the Bremsstrahlung, or characteristic radiation in the Bremsstrahlung. Now, why do we talk about this X-ray production here? Because what type of light model are we using when we're talking about the X-rays? The wave or the particle? And yes, Sarah, you were right. She said one word and I said a different one, and that makes you think you might be wrong. So that's why I clarified that she was right the first time. Which model are we using? Wave or particle? A particle, because we were treating them as photons. Photons are the particles of light. So this was another example of a particle nature that we can see exhibited. Okay, so you have questions?
So just out of curiosity, I see that the gamma and X-rays are kind of like overlap. So does it just depend on characteristics at that point, or how do you determine?
Source is what I use. X-rays are from core electrons in an atom. Gamma rays are from the nucleus of an atom. So they come from different sources. So an X-ray and a gamma ray can have the same frequency, but they have a different name because they come from a different source. And in fact, ultraviolet, all of this is ultraviolet. So X-rays are ultraviolet and so is gamma. Yeah.
So if they have the same frequency, wavelength, do they have the same characteristics?
Yeah.
At a certain point?
Yeah, it's electromagnetic radiation. There's no distinction.
Okay.
It's just the source is why we have a different name. So if you use a radioactive isotope that produces gamma rays of the same range that your X-ray machine does, it works the same. Okay, so particle physics is the reason, or particle physics, the particle nature of light is the reason that we looked at the X-rays here to see, yeah, it's another example of particles. This is an equation that was enormously useful to me in graduate school. I was working with an Excimer laser. Anyone ever heard the name Excimer? Nope. Excimer means excited dimer. We use things that had like, krypton fluoride. I did most of my experiments with krypton fluoride laser. Well, if you look back there, krypton is a noble gas. What makes a gas noble?
Filled valence electron.
Completely filled valence electron. So how does it react with other atoms? It doesn't. We call them the inert gases. Unless you motivate it. If you excite it, then you can make it bond. So krypton fluoride forms a bond if you excite it. And so the excited dimer, you make a dimer with krypton fluoride, and then when it de-excites, it breaks apart. And we didn't talk about lasers, at least yet, but for a laser to work, you need to have an inversion layer. You have to have a higher population in the high energy state than the low energy state. For an Excimer, there is no low energy state. So you always have a higher population in the higher energy state than the lower energy state. But why that was useful for me was because my laser had a frequency of 248 nanometers. What range of light is that? Is that visible, for instance?
No.
Oh, that's not a frequency. That's a wavelength. Whoops. Did I say frequency or did I say wavelength? Oh, boy. Had a wavelength of 248 nanometers. It's not visible. We have wavelength up here. Nope. Yeah, we're up here. So this here is about 400 nanometers. So it's here in the ultraviolet. So it's an ultraviolet laser. I couldn't see the laser, which is part of the reason why I'd come home with sunburns on my arm. I couldn't see it, but it reflected off of everything, and so it reflected and hit my arm and give me a sunburn. I had rectangular sunburns all over me. So we talked about it as 248 nanometers usually. But then when we talked about the energy levels of defects in our materials and the band gap, we talked about those in units of electron volts. And so I had to go through the calculation of converting the energy to electron volts. So notice the energy is HF for photon, and frequency is C over lambda. So that's HC over lambda. And so if you want to convert between frequency, so HF equals HC over lambda, we can cancel those H's, of course. That's not very, oh no, we don't want to cancel the H's because I wanted to convert from frequency to energy, or from wavelength to energy. And so I had to take HC and divide by the wavelength. And so if I take H is 6.626 times 10 minus 34 joules times seconds, multiplied by C, the speed of light, 3 times 10 to the 8 meters per second. That's going to give me units of joules. And then divide by wavelength in meters. That'd give me units of joules. But I want units in electron volts, and so you have to use that 1.602 times 10 to the minus 19 joules per electron volt. And if you multiply it all together, HC is 1240 nanometers times EV. And so then I could just say, okay, my energy is equal to 1240 nanometers times electron volts over 248 nanometers. And if you do the calculation, well, my memory says that gives me 5. And so the photons had an energy of 5 electron volts. It had a wavelength of 248 nanometers and energy of 5 electron volts. So that was very useful to me in my research. And I think I'll have that number on the test. It might be useful on the test if you want to go from wavelength to energy. Okay, just a quick question to make sure we got the topic of X-rays. What causes the characteristic peaks in an X-ray spectrum? Electrons falling to lower energy states. Bound electrons falling to lower energy states is exactly the right answer. So that's what's causing these. What's causing the Bremsstrahlung? Okay, was that D as in dog or B as in boy?
D as in donut.
D as in donut. It's actually electrons slowing down. The Bremsstrahlung is the braking radiation. So slowing down. Okay. Comparing wave theory and particle theory. So this is asking about wave theory. I'm going to have the same question with the same answer options, I think, for particle theory. Which statement is true about wave theory? So one of these is true about waves.
Not necessarily.
A, the frequency of a wave cannot change. If I have a wave that goes from, let's say, air into water, the frequency stays the same. The speed didn't stay the same, so the wavelength changes. But the frequency stays the same. First semester, I talked about having waves tied on a string. And so I have a heavy string and a light string. I have the string oscillate. If the frequency changed at the knot, my string would have to actually break at the knot, right? So that they aren't traveling up and down together. So in order for it to be continuous, it has to have the same frequency no matter where it goes. So one of our rules for waves is the frequency cannot change. The wavelength can change as you go into a different medium. The direction can change, you refract it, reflect it. But the frequency can't change. Now, we didn't talk about momentum of a wave. Why not? Waves don't have momentum, but particles do. We didn't talk about the energy of a wave. Well, we talked about the intensity. But we talked about the energy of a photon, momentum of a photon. Well, did we talk about the momentum of a photon? Mm-hmm. I know we talked about the energy, and we learned that
I think momentum is just in our reading quiz. I don't know if we've talked about it.
I think that was the equation that we had last class period. I hope it's right because I'm going to go with it. So if that's true, then I should have the momentum of a photon is equal to VE over C squared. Now, what's the speed of a photon? Assume we're in vacuum.
Speed of light.
Yeah, speed of light. So the momentum for a photon is its energy over C. But we just learned the equation for the energy of a photon is HF. So there's the equation for the momentum of a photon. So momentums have photons. Photons have momentum. Now, when this idea, Nate, I'm going to have you do this. Can you go get that little toy that's in the window in my office? When the idea of photons having momentum was introduced, what does any good physicist want to do? Calculate it, sure, but calculations only go so far. You don't convince people with calculations, do you? Yeah. You do experiments. You want to measure it. Now, I'm having him bring in the thing that was created to measure it. Not bringing out a light because I don't know where the nearest light is. But this little device was created to test this. So he's going to bring it in a second. On one side it has panes, little sheets of metal. And one side is painted black. One side is painted silver. So if a photon hits the black side, what's it going to do? What happens when light hits something black? It's absorbed. And so its momentum will be completely transferred. That's it. What about when light hits the silver side? What's going to happen then? It should bounce off. But if it bounces off, the change in momentum for the photon is, let's just assume it hits straight in and comes straight out. It's going to be twice its momentum, right? And so if you shine a light on this, it should, if light has momentum, now that there is simply because of me shaking it, it's not a response to light, sadly. It should move away from the silvered side because you had twice the change in momentum when they hit the silvered side and when they hit the black side. And so this was made, and people shone light on it. And what did it do? Guess.
It agreed with the theory.
No, went the other way. And so like, oh no, what could it be? And so eventually they realized the problem was this wasn't perfectly evacuated. There's some gas in there. And so a famous physicist who, fortunately, I don't remember his name, fortunately so I don't besmirch his reputation, he wrote a paper about the black side heating up more, and thus the molecules that hit it will leave at a higher speed, and so it's not the light anymore because the momentum of the molecules is much higher. And so then it's being propelled away from the black side by that. And then other people said, no. Logically, those molecules that bounced off of the hot side are going to move around and bounce off of the other sides as well and transfer the momentum back. So on average, you actually don't get a net kick out of that. And so that can't be what's making it move. And so somebody wrote a paper that had the correct explanation. The correct explanation is that molecules that hit the sides of this get transported across it, and that's what's giving it its momentum, making it rotate. And it was sent to the person, the famous physicist who had written the wrong explanation. You guys probably don't know this much about scientific communication, but when you write a paper, the process works right. You might have read right. It's supposed to be sent to a reviewer or a set of reviewers who then go through and read it and say, oh, this looks sound, or oh, this has some problems. And it doesn't get published until the reviewer approves it. Well, this paper was refuting the reviewer's own paper, and so he sat on it. He didn't return the paper. And then the guy who wrote the paper died, and then he submitted the paper with his own name. Yeah, nice. Anyway, this is something that was designed to measure the momentum of light. It failed. Now that we can achieve lower vacuums, that is, pump out more gas, they can make them so they work the way they're supposed to. When I was in college, for our advanced physics class, one of my classmates actually did an experiment to measure the momentum of light. Using a laser beam, hitting a piece of tinfoil that was suspended by a torsional string, and measuring how much that tinfoil rotated, he could use the power in his laser beam and the frequency to calculate how much net force, change in momentum per change in time, was being applied theoretically, and using the rotation measure how much net force was actually there. You had a question, Trish? No. Did somebody, Leslie?
So I know this is like going back to the little story thing, but just out of curiosity, how did they find out that it wasn't him who wrote the paper?
I don't know. It's a story I read. I don't remember the name, so it's good, because if the story's wrong, I'm not, besmirching somebody's reputation. Compton scattering. Arthur Holly Compton made a very interesting discovery. He was scattering light, and so he had light hitting his sample, and if the light went straight through, his frequency stayed the same, or his wavelength. We talk about this in wavelengths. The wavelength stayed the same. But if the light was scattered at a different angle, he had two peaks. One peak that was his original wavelength and one that was a new wavelength. And the more the angle of scattering, the bigger the shift. This is a problem. The frequency is measured in air, or the wavelength is measured in air. And we just saw that for a wave model, the frequency cannot change, right? We have two wavelengths, which means we have two frequencies. And so we have a shift in frequency. If you have a shift in frequency and the wave model says you cannot have a shift in frequency, what does that mean?
Your model's broken.
Your model's broken. It's not behaving like a wave. But we do have a particle model now. And so he went using relativity and calculated and found that what was going on was that, so here's that same question about particle theory. I can see when people put stuff away. We have to end soon. If you have scattering and you treat the light as a particle with momentum of E over C and energy of, E over C, that's HF over C, and energy of HF, it hits an electron. The electron is going to scatter because you have transferred momentum, and the photon is going to scatter to a different angle because you have a change in momentum in this direction. And so using conservation of momentum combined with, you can't just use conservation of momentum combined with conservation of energy, he was able to calculate that, you see we've already gone through this, that the change in wavelength, so wavelength prime is the new observed wavelength, and then minus the original wavelength, so that's the change in wavelength, is equal to Planck's constant over the mass of an electron times c. That thing out front, Planck's constant over 8 or over mc, we call that the Compton wavelength. It has a value of 2.4 something times 10 to the minus, I think it's 10, times 1 minus cosine theta, where theta is the angle that it scatters, the deviation angle. So the Compton wavelength, where do I have it written down? Here we go. Not minus 10, that's minus 12. The Compton wavelength is 2.426 times 10 to the minus 12 meters, or minus 3 nanometers. And so this here, once again, is strong evidence for light behaving as a particle. So we've now seen 3 different things that are evidence for light behaving as a particle. I've got to quit. Have a great day. I'll see you on Friday.